Welcome back. My name is Daniel Weiss. I'm the Chief Scientist of the Ministry of Science and Technology and Richmond Distinguished Professor of Aerospace Engineering at Technion. It's my pleasure and privilege to open this first space science session of the Ramon Conference. As a member of the board of the Israel Space Agency from its start in the 1980s, I'm happy to see that we now have about 750 people in the audience here, 750 people at least interested in space. And as we speak, the Israel Space Agency is signing an agreement with the European Space Agency, which we see as a giant leap for Israeli space science. In the present session, we'll hear from the proponents of manned exploration, as well as robotic unmanned research, from the very best speakers. So we can look forward to an exciting 2 hours. We are starting about 15 minutes late, so lunch will be 15 minutes late, and I'm asking all the speakers to stay within limits, because people, when they start getting really hungry, there might be a problem. Is Professor Southwood in the room? Okay, great. Professor Southwood, who will speak about ESA space science programs, is our first speaker. And let me introduce him very quickly. He was appointed ESA Director of Science and Robotic Exploration 2 years ago. And after graduating in 1966 in Imperial College, he went on to obtain a PhD in physics from Imperial College, and then did a postdoc at University of California in Los Angeles. From 1971, he's been in Imperial College. He became head of the Blackett Laboratory until 1997, when he joined ESA as head of Earth Observation Strategy, and he introduced a new program in Earth science, which we all know, the Living Planet. In 1999, he returned to academia to become Regents Professor at UCLA and then at Imperial College, and then in 2001 came back to ESA to lead the space science program, and which has now been enlarged to include robotics. Professor Southwood, please.
All right, thank you very much. I always find myself a little surprised to hear myself described. Anyhow, it's an enormous pleasure to be here and to speak in Israel, and to speak on a topic that I think is very important to all of us. And I'm happy to say some of the themes I'm going to elaborate were raised both by the previous speeches, by President Peres and by Rabbi Professor Hershkovitz. I work for the European Space Agency, ESA. Everybody knows what ESA stands for. The S is for science, the A is for applications, and the E is for exploration. Those of you who speak French will be able to easily translate that into French. Exploration, science et application. It's a full-service space agency, as my Director General explained, but as I showed, science is psychologically at the center of it. And I think it is very important to understand that. Try and remove that, and you lose the other two. I want to raise the issue of why we should pay for science, and I can tell you it's necessary, but I want to give you some ideas as to why it is necessary, or indeed, I would prefer that you thought for yourself why it is necessary. It is a little, as Laurie Garber said, quoting the American president, of an airplane without its engines. My budget is around 15% of the agency budget. I think that is a just proportion. I think, however, we need to keep remembering that we get public money to do space science and exploration, and so we must continuously sensitize ourselves to why we should use so much public money on something that, if you like, seems first and foremost interesting to scientists. I think that is a very false understanding. To give you, if I were NASA, I would be talking about the future. I'm ESA. I really want to get you to realize that in the last decade or decade and a half, ESA has really stepped up to the mark in space science. We have here images of spacecraft we have in operation. In one of them, Hubble, we're a minor partner, 15%. But then in SOHO and Cluster, the United States is a minor partner with us. That, for me, is what partnership is about. You play to your strengths. Sometimes one partner leads, sometimes another. We are covering the universe, as my Director General said. We have astronomical observatories like Integral, a gamma-ray observatory, jointly with Russia. We have Newton, an X-ray observatory, a complement to the American Chandra mission. We have our own way of going to comets. We go there and just, in the European way, just tickle the comet behind its ear. Scratch and sniff, not the bang, you're there approach of our dear American colleagues. We had Ulysses. Ulysses is now finished, I'm sad to say, which flew over the poles of the sun, again jointly with the Americans, and in fact the first mission where the Americans were truly minor partners with us. That's not to patronize the Americans, it's just to tell our American colleagues we're growing up, and that's part of growing up, taking on our share of the burdens. We've been to Mars, to Venus, we're going to Mercury with the Japanese. Again, a first step, a major change in our international cooperations. We have a variety of other cooperations where we form small contributions with China, Double Star, but in addition, Chang'e 1, Chang'e 2. We cooperate with China, with Chandrayaan, with Japan, with Chandrayaan, with India. Really, space science, one virtue of it is neutral territory. It is the whole universe belongs, in a sense, to every human being. And so, really, we can use space science as territory to learn to work together. Hopefully, that then teaches us how generally to work together in more complex things. I want to particularly focus on Herschel and Planck because after 10 years as directing the science program, that was the 10 years in which we built these two great observatories. Only recently, perhaps the rest of the world realizes, I'm afraid I learned it from the day I signed on as the Director of Science. We got two enormous cryogenic telescopes. I have to say this, I can see at least one American in the audience smiling at me. We have now the biggest telescope in space. 3.5 meters, envy the diameter. And in fact, we're going to keep that laureate for a long time because to build a monolithic mirror, 3.5 meters fitting inside the fairing, the biggest fairing that you can launch, of course, the biggest fairing is 4 meters. We feel pretty safe. We've got the largest telescope in space. Planck is also a telescope off-axis, 1.5 meter. Again, cryogenic. Cryogenic is one word, but boy, does it place complications. Both these spacecraft function at close to absolute zero. And I can tell you that is not a natural temperature in which to function. You have to work very hard to get to absolute zero, even in absolute space. Herschel is to unlock the secrets of star and galaxy formation in unexplored wavelengths in the infrared and the submillimeter. You know these wavelengths. When you walk through a door that opens automatically, that's infrared. When you use a microwave oven, I'm afraid that's submillimeter. We're looking at the universe and things you use every day, and I'll come back to that issue because it's very important. And Planck goes back even further in time and further away, as my Director General said. We're going back to look at the cosmic microwave background, which is left over from the Big Bang. And as Rabbi Hershkovich said, we know we all came out of that. And that's one of the joys of being my age, is that I'm old enough to remember when we didn't know that. And that really is the big change, the massive change in the universe. It's in my universe, it's in your universe, since I started. 2 spacecraft, 2 cryogenic payloads. In fact, I'll say the Planck coolers take the detectors at the heart of Planck down to 0.1 Kelvin, 0.1 degree above absolute zero. And as a result, something else we can claim is, I know Tel Aviv is supposed to be a cool place, but honestly, Planck's coolers take it to be the coolest place in the universe. Okay, why do we do it? Well, because the universe looks very different when you look at it at wavelengths that we cannot see, we cannot use with our eyes, nor can we use with our ordinary telescopes on the surface of our planet. Happily, our planet has an atmosphere. Unhappily, for us who want to know more about where we came from, we can't see through that atmosphere except in very narrow windows in the electromagnetic spectrum. And so, happily, our eyes work in that window, so occasionally it's very nice to come to Israel and see the sun. There's a rumor it's there when you live in France. It's nice to see for real it's there, although you put on a show this morning that reminded me of home. But really, space has opened up our universe in unimagined ways until we got above that atmosphere. And it remains incredibly important that mankind keeps the capacity to go up there. I've already said that, so rather, I think, show you the sheer scale of what my agency is capable of. A very large telescope, 3.5 meter. You can see that it's more than 7 meters tall. Those are human beings, and not particularly short human beings, standing beside it. They built the spacecraft, and indeed they're now looking at the door and wondering how to get the spacecraft out. Happily, we looked the other direction and found there was an even bigger door. So I think I'll move on and give you some of the immediate wonders we got from Herschel. I think, actually, there's a slide. Let me just check. No, there seems to be a slide missing. But really, one of the first conference we held, really about 8 months ago, it takes a while for scientists to absorb the information that comes down. and that's only correct. They can always tell you before something is launched what they're going to find. That's because they've had to learn how to raise money, and you can't raise money without telling people what you're going to do. But actually, once you get the data back, inevitably, sometimes you find something you expect, but equally well you have to integrate it. Science is an interface. It's a man-machine interface. You have to then work with your brains to bring out really what you have found. Here was showing protostellar, pre-stellar cores forming out of cosmic dust. The only way to see this is in infrared light. And what is quite remarkable is to see these pre-stellar cores. Actually, it's telling us something about the way stars begin and galaxies form stars. You see strings, cosmic strings, not, I'm afraid, what some of the theoretical physicists talk about, but really showing us that our universe, however uniform we believe it should be, isn't. That really it's important to understand why things form in a structured manner. Out of a big bang comes structure. Structure that ultimately brings me to be talking to you today. I'm now going to do something that's very unwise, and that's show you spectroscopic results. And indeed, show you really what Herschel is capable of. Look at the numbers along the bottom there. That's all you need to retain from this slide. 600 through beyond to nearly 2,000. Just remember that. You see, there are features there. Lines. These aren't beautiful images unless you happen to be a spectroscopist, unless you happen to be a physicist or a chemist trying to decode what is going on in the cosmos as we see it now, but also went on in the past and led eventually to us, to the formation of our planet and the formation, ultimately, of life on that planet. These lines, we now can expand, and you see now we go from 480 to 640, and there are even more lines. This gives you an idea of the quality of our instruments. And then to blow it up further, taking again a tiny segment, magnifying it, look at the detail. 520 to 530. If those of you, you'll notice that's in gigahertz. They're just, the numbers are the important thing. Look at what we're able to resolve. And this is a cosmic fingerprinting machine. I can go on, 520 to 524 gigahertz. Still, features are emerging. We're peeling away. And ultimately, then starts the work of the physicists and the chemists, who can then start identifying the lines. Most of them sound extremely unpleasant. Methanol, hydrogen sulfide. Hydrogen sulfide smells terrible. Bad eggs. No, these things, these complicated molecules that we're detecting in space, I'm afraid, are the stuff of life. What we're seeing up there is the creation of things that I'm afraid are going to be necessary later on for the creation of our planet, or rather for the creation of its habitability, for the creation of us. I'm afraid it looks perhaps inelegant, it looks rather dull, just strings of lines, but I have to tell you, this is extraordinarily important. Let me also now bring Herschel and Planck together. Why did we build them together? Well, they are linked. Herschel is an observatory, and here we're open for business to cooperate with astronomers in Israel, and I'm sure that's going to happen. Herschel, anyone, in fact, on the planet can make a proposal. It has to go through a lot of review to get Herschel to point at a particular object and to make the case that here is, I have to say, because this thing cost around €1 billion, to make the case for doing universe-changing science. When you spend that much money, you have to change the universe. You have to open up the universe. Planck looks on a much larger scale. It doesn't exactly see the whole sky at once. It slowly rotates, and over 6 months rotates in such a way as to map the whole sky. As a result, we've got a much wider field of view, but of course we can use it interactively with Herschel, which looks at details. It's a very productive thing to do. My Director General already showed you this image, and of course what Planck is after is what's hidden behind this image. We have, happily perhaps, a galaxy we live in, the Milky Way. We have other galaxies between us and our very beginning in the Big Bang. In the polar regions, where the image is sort of red and orange, that's where we're trying to go. Okay, I didn't realize I had so little time. I'm going to move on. Really, if I've impressed you with our capabilities and our cosmic vision, that's our future. I must come back now to exploration, a human endeavour at the moment now done by robots. Their international cooperation is at the core, and very much, I think, a human endeavour. Here is what I felt when we first saw the images of the surface of Titan. A poem by John Keats, another Englishman. There's no cure. Then I felt like some watcher of the skies when I saw when a new planet swims into his ken, or like stout Cortez when with eagle eyes he stared out at the Pacific, and all his men looked at each other with a wild surmise, silent upon a peak in Darien. I learnt that poem at school and never dreamt I would actually feel it. This is what an explorer feels. However, there has to be much more. There has to be the first images we saw of Venus. Okay. The way we looked at our sun for the first time 24 hours a day, 7 days a week. The fact that now we're going to explore Mars together with our American colleagues. That's, for me, a step that can only expand to include other nations. That joint program, I think, is very important, but why we got continually to bring things back to home. Those techniques I was showing you for looking at the cosmos, for looking at 1/1,000,000th of a degree scale things on the cosmic scale, tiny things, we use every day. We use them to make our daily life more secure. We need to be driven by the demands of exploring our universe to bring new technology, new techniques, and new creativity back here on Earth to make our life more peaceful, more secure, and really continue the challenge of being human beings. I very much thank you for the time, and I look forward to Israel joining us in the European Space Agency in the further exploration of our universe. Thank you very much. Thank you very much. Thank you.
מצטער, אבל בגלל קוצר הזמן לא יהיה זמן לשאלות למרצים, אלא אם כן מרצה יקצר, נראה מה יקרה. הנושא הבא, our next speaker is Colonel Creamer, who will talk to us about the space station as a laboratory. Timothy Creamer, Colonel Timothy Creamer is an astronaut. He has a BS in chemistry and a master's in physics from 1992, and then was in the Air Force, in the U.S. Army, sorry. In Israel we only have that. In the U.S. Army, and was assigned to, for example, the 82nd Airborne Division as commander of an air cavalry troop or so. He then finished his master's at MIT in 1992 and was a lecturer at the Department of Physics at the United States Military Academy. He then was assigned in 1995 to Johnson Space Center as a Space Shuttle Vehicle Integration Test Engineer, and reported for astronaut training in 1998. He launched above the Soyuz in December 2009 and logged a total of 163 days in space. Colonel Creamer, please.
First and foremost, thank you for the wonderful introduction that I got. And more importantly, to distinguished guests and dearest Rona, it's my honor to be here, and the best word I can find to describe the feeling of speaking with you and sharing with you is utter humility. It is wonderful to be here. The goals and the aims of the conference to look forward into the future to better humanity and to offer the hope and goals to our children and our children's children are what have also inspired us along our journey. In terms of having jobs and focuses that we can deal with and work with every day, I have to say that I think I've got one of the better jobs in the galaxy. And what I'd like to try to do is to talk about some of the science that we really haven't spoken yet about, but we've alluded to. We've heard about a globe called the Earth without borders, and people sharing their hopes and dreams together and moving forward into the future. We've heard about science and the explorations in order to understand the nature of the world and the universe about us. But we really haven't seen one of the most active experiments yet, and that's what I'd like to share with you now. I would offer you the thesis that we are the experiment. We on Earth, to be successful, are the experiment, and we on the International Space Station are performing an experiment of simply living together. I am blessed and fortunate to have worked with a very multinational crew, and we had an absolutely astounding time. So let me see if I can share with you that experiment of living together and working together as multinational crewmates and training together in that business. So if we can roll that video, I'll see if I can share with you the 5.5 months of excitement and joy that we had between December and June of last year. When I got up there, we were Expedition 22. Maxime Sarayev and Jeff Williams waited for the three of us to arrive, and then once they left, we became Expedition 23. And like all good space stories, you have to start with a rocket. Otherwise, it's just a story, but this is a space story. And so this is December 19th in Kazakhstan. And as you can imagine, in Kazakhstan, on the steppes, December 19th, it is extremely frigid and cold. And the family and friends that accompanied us there keep remarking just about how cold they were. As you can see, it's a multinational crew. We had a Japanese flight engineer, a Russian Soyuz commander, and me. And we go through this typical press release interviews and stuff, and I get asked here, what am I going to miss most? And I ended up saying, bubbly water. You can't have bubbles in space, you know. So, there's a tradition that on the day that you launch, you sign the door of the room that you were living in down in Kazakhstan. And here is Soichi signing his door, and then he does something remarkable. He draws his flag. So here I go. I'm signing my door, and I'm going, do I need to draw my flag? Oh, no. Not going to do that. So we walk on out to the commission, and we report that we're finally trained and ready to go in these well-tailored suits. And we get up to the launch pad, and we're in specific order, and Oleg's ready to go. He goes, up, come on, up, go. And as good, dutiful crewmates, we turn around and wave some more.
מנופפים בידיים, עוד קצת.
So now we sit for about 3 hours.
אז אנחנו יושבים כ3 שעות בקפסולה הקטנה הזאת. תכניסו 3 אנשים בגודל אקסטרה לארג' לתוך האמבטיה שלכם, וככה זה מרגיש בערך. והמתנו, וחברי המשפחה שלנו עומדים בחוץ ומתקררים עוד ועוד. מדובר ב-21 בדצמבר, ואתם תראו עוד מעט עד כמה.
We got rain and sleet and snow, and we're going to launch anyway. And when I ask my kids what they remember most about the visit to Russia and Kazakhstan, they both say that the launch was spectacular, although it was really cold. So it takes us about 2.5 days to race and track down the space station. And after the 2.5 days in this tiny little vehicle, we approach the station, and Max and Jeff are on board taking these pictures. And then for the Soyuz, of course, we've got a primary and a backup system, and then, of course, a manual way to rendezvous. And for us, we were very fortunate. All the systems worked as advertised, and so we were able to sit there and monitor the approach. And this is the view that you get when you're sitting in the commander's seat. And then Jeff and Max are taking these pictures again of our approach. So not too bad when you consider it. 2.5 days later, we get to the point where we're accurate enough to be able to dock the space station. And this is real time. This is how slowly we come together for sure, in reality. And the docking is complete. And we are now arriving on December 23rd. And Max is going to open up our hatch here for us. And of course, since it's December 23rd, we have to come prepared for Christmas. And here comes Santa Claus Suichi. And he was very popular because in that knapsack that he has is all the fresh food for Max and Jeff. And shortly after Suichi comes Santa Claus's happy elf. And almost immediately after arrival, the first thing we do is we end up having a press conference. And one of the nice things is you get to talk to the families that are in Moscow, and they were at the control center for the rendezvous. So we're having our initial press conference, and then shortly thereafter we have a second press conference, and Max is going to show you what microgravity looks like. And I think we should all go to work like this. Now, for those of you who wonder about space aliens, you can see the shadows moving on the background there. And to dispel any rumors, that's really not space aliens, but Max and Oleg had to go outside to do a spacewalk in order to prepare for the arrival of a Russian module later on in our increment. And so they're doing the cabling and the hosing, and they're setting out some external experiments for that spacewalk. Back in the Russian half of the station, we're monitoring an incoming progress resupply vehicle. And if everything goes well, again, it's just monitoring. It's an automatic docking. This progress arrived nicely. We had a second progress in our mission, which was slightly exciting, and it didn't behave nicely. Jeff Williams and I are doing a commercial spot for a show called Dancing with the Stars. Buzz Aldrin was competing on Dancing with the Stars, and I mentioned here He's the original moonwalker, but can he still do this maneuver? Every day, our goal is to do science experiments and utilization. And every day we have to work on logistics. And this bag here is a bag that, of course, has something in it of an import. But most of the time, most of the overhead in the day is dealing with logistics. And here, I lost my footing, and I just didn't really care because you can't fall down in space. So I just continued to rotate and work on whatever it was I was working on. Science experiments like how to better grow plants. Max was working on growing lettuce and wheat. This is not only for possible duration of missions that go farther away, like to Mars, but also how to improve what's being grown here on Earth as well. Soichi is practicing his zero-G swimming, because later we have to do synchronized swimming. You put two helicopter pilots together, what do you get? We're doing what's called Saturday Morning Science, and we're doing a bit of an outreach to schools and talking about conservation of angular momentum, and this is the familiar ice skating problem, done with a zero-G twist. Well, it's come time now for Max and Jeff to depart, and so we have to say goodbye and do a change of command. And anytime you do hatch closings or hatch openings, you have to do hugs and kisses. And it's because of this video that I finally understood why I found my camera in the next module over. So Max and Jeff are in their Soyuz. Oleg is going to assist them in closing the Soyuz hatch. And so we don't have a great big hole when they leave. We have to close the station hatch as well. And now we are 3 people for about 10 days all by ourselves, and we get to do fun things. We get to pull out the fresh food we had hidden from Jeff and Max. We get to make breakfast tacos or breakfast burritos, and the trick here is to use bread that is not crumbly, so we're using a tortilla. And the other trick is to put the sauce down first so it acts like a glue to hold everything on. We do haircuts. Alex told me to go cut Soichi's hair, told Soichi to cut my hair, and then Oleg looked at the both of us and went, TJ needs to be the barber. So, doing normal house cleaning things, and of course, if you don't have a vacuum cleaner, you lose all the hair, so that's what the long hose was. Typical playing with water, fun stuff. I'm trying to get rid of bubbles in water so that the pumps don't cavitate. And 10 days later, the new crew arrives, Sasha, Misha, and Tracy. And one of the fun things about new people is they always knock things off of walls. Watch Oleg, he's just going to reach up and put that back, just nice, right there. There's Misha and Tracy. And of course, the rule is whenever you open a hatch, you have to do hugs and kisses. So that's what we're doing. Now, while I was up there, we got visited by 3 space shuttles. This is actually the second of the 3. And when the space shuttle comes up, it hovers a little bit away from us and does this RPM, R-bar pitch maneuver. And we're doing a very tightly choreographed photography survey of all the tiles. And we will take these photographs and we'll downlink them to the ground so that the ground can analyze to make sure that there are no tile damages for the shuttle's return. Here's the RPM maneuver from the shuttle's vantage point. And when this shuttle arrives, they open the hatch. And this is a very momentous moment for Japan, actually. We have Soichi on the station side, Naoko on the shuttle side, and this is the first time that Japan has had 2 astronauts in orbit together. And of course, once you do the hatch opening and you get all the equipment out of the way of the hatches, you have to do the obligatory hugs and kisses. And the nice thing about hugs and kisses in orbit is that it doesn't really matter what your orientation is, it's very easy to do. And once again, as we go back and do experiments and get back to work and stuff, we have to do logistics over and over again. And no kidding, this was completely fortuitous. When we put this video clip in here, it's the same bag that I was working with last time. Naoko weighs about 90 pounds, and this rack weighs about 1,800 pounds. And so you can see, of course, in a microgravity environment, it's very easy to maneuver very massive things if you go slowly. And they're going to put this into its birthing place, but we're going to speed up the video here just so it goes more quickly. And you can see, because Naoko weighs real fast. This is a wharf. It's a window observational research facility where schools can actually control cameras in the big laboratory window and take Earth observational photographs. One of the major events for us during our increment up there was the assembly and the checkout of something called the small fine arm. This small fine arm goes on the end of the Japanese robotic arm, and it has a couple of little fingers, which you'll see here in a close-up in a second, that allow it to do extremely fine work and grab bolts. Soichi and I are now making sure that all the joints behave the way they're the little fingers. All the joints are behaving correctly in the right direction, the right magnitude. And it was an extremely successful checkout for us. Soichi here is working with what's called Melfi. It's a minus 80 degrees Celsius freezer where we stick a lot of our biological samples until the shuttle can come up and take them. So Soichi is taking them from Melfi and putting them inside another little thermos to be returned on the shuttle and analyzed on the ground. And one of the nice things about working with Melfi is not only is it extremely cold, but when you get done working with Melfi and you're going to put the tray back in, you get to experience what we call the poof maneuver. You'll see that here in just a second. Here comes the poof maneuver. Poof. On Fridays, we would have conferences with the ground, with the control team, and I was able to get started a little tradition where we're wearing red shirts for Fridays, and the ground joined us. And we would have a video conference, and Oleg is the commander here. He would often let me chit-chat with the ground, so we would hold the conferences in the lab and discuss things with the ground. Speaking of science, I volunteered a lot of my weekend time to put together facility experiments. This is a fluids experiment that was not operational when I got up there, and it took 2 or 3 weekends to actually assemble it, put it together, and get it operational. This rack is in the Japanese module, and once again, we were using some of our own time to put the experiments together so the ground could do the remote control of the experiments. The shuttle guys had some downtime, so they played baseball. Clay hits a homer, and he's going to run around the bases. This soccer ball actually made it to the World Cup. The shuttle crew flew it for the World Cup. And Soichi is going to be so happy because he actually scored. Soichi and Naoko hosted a sushi dinner for us, and the reason why that's special is because it has to be very fresh food, and we really appreciated fresh food after being up there for 4 months. Exercise is important. 2.5 hours a day we exercise. It's not like on the weightlifting machine in weightlessness. Back in the Russian segment, we typically shared our lunches back in the Russian segment. And we get ready now again for the third of the 3 shuttles that come up. And this shuttle is delivering the Russian module that Oleg and Max were doing the spacewalk for in preparation. This is real time. This is how slowly we come together. And of course, after hatch opening, you have to do hugs and kisses. Yeah. Garrett, you may have recognized Garrett there. Garrett stands about this tall. So when I could let him go in a module and he couldn't touch a ceiling or floor or any walls, we could just leave him there for a while. Their primary mission was to deliver what was called Mimadim, and this is the robotic operation that actually docks that module to the space station, completing for the most part the Russian segment. Soichi, talk about international crews. Soichi is working on an experiment in the European module, and he's changing out samples to be returned back to Earth. I worked with some plants, and these fir trees I pulled out. The air goes back through the hatches back to the Russian segment. Within about 2 minutes, the Russians come down to our half of the station and say, "What smells so good?" Cleaning is a weekly thing, and here's Soichi cleaning. And one of the nice things about our time together when we were up there is that we were able to see what's called the window to the world, the cupola, this 7-windowed window. And we were up there for April 1st, April Fools, so we had to do a small little joke with the ground. But this is a wonderful window to do Earth observations with, and this is where you get to see what the world looks like from a very nice vantage point. These photographs are unretouched. This is how we take the photos. Here's Crete in Greece. Central Asia, or the Stans. It's sometimes an amazing view and vantage point that you look out. You can even see dust storms, and it's incredible. It just takes your breath away. Here's Cuba, Florida, the Bahamas, probably one of the top 2 places that gets photographed. Patagonia is another place, a lot of the Mediterranean also. A real live moon set from our vantage point. This is Japan at night, and I don't know if you can see it or not, but I left this clip in so that you can see how many dead pixels there were from the camera. And the dead pixels are from a camera that's been up in orbit for a while and had been hit with radiation. This is Washington, Baltimore, and Manhattan at night. Wave at Luigi. All right, it comes to be our time to return. And so we're going to take a tour from the U.S. laboratory back towards where our Soyuz is docked. So we're going to go through Node 1, and you get to see all the open stowage, because we don't have a whole lot of stowage room. Logistics becomes the real key game in town to make everything efficient. This is where we keep all of our extra clothing and articles that we use every day. And as we head back into the Russian segment, Russian half of the station, you can see more open stowage. These are all food containers here. Now we get into what's called the service module, really the command post for space station. And Oleg's getting ready for our departure. And Sasha and Misha are back in the bedroom area here. And we're going to keep going back to the back, and our Soyuz is docked on the very end. We get inside the Soyuz and we say goodbye to folks. And from the time that we undock, 4 hours later, the search and rescue folks that find us will open up our hatch. Speaking of which, for this landing, it was the first time that the search and rescue forces were at the landing site and were able to set up a video to capture this. We knew we were down. Those were the soft landing thrusters that fired. Also a first-time event is this still photograph. Bill Ingalls takes this picture. It's a moment. It's a fraction of a second before landing. He gets this just to capture the soft landing thrusters. This term, soft landing thrusters, it's a misnomer. And so now the Russian search and rescue forces are able to pull us out. And our gyros, our inner ear, are really, really, really unstable, and we are very dizzy at the moment, but we kind of expected it. But it's so good to have the hatch open up, and you get to smell the fresh air of the steps. A Russian poster that they superimposed our faces in, which was kind of nice. And then this portion of the video will run for a while, so I just want to let you know that this is not computer animation. This is actually a fly around by the space shuttle as it takes photography, video photography of the space station. Each time that the shuttle departs space station, assuming that they have the fuel to do so, they will do a fly around so that we can see the wonder which we call home, but also backdropped against the border of this earth that we were able to witness for the 6 months we were up there. So I hope that gives you some idea about us beginning the experiment on orbit. And if you go to YouTube, for instance, you can see a shorter version of this where the theme really is Together is the Future. As I introduced this talk earlier, what is inspirational about this conference is we're talking about the benefits for tomorrow, benefits for the generations to come. And together, I think we can do that in the future. Thank you much.
Thank you, Colonel Creamer. Next, we have our own Ehud Bachar, head of the Asher Space Research Institute at Technion, and he's going to scale up. Now, up to now, we heard about the laboratory at the space station. He's talking about the universe as a laboratory. Professor Bachar finished his PhD in 1999. Spent 3 years in Columbia and then returned to Technion in 1992 and has been head of the Asher Space Research Institute for the last 2 years, I think. Udi.
I must say that I'm still not sure if I'm supposed to speak in English or in Hebrew. I was asked to speak in Hebrew. So that's what I'll do. עד שמחברים אותי למחשב, תנו לי רק להגיד תודה לדני על ההקדמה ולמכון פישר על ההזמנה ולכל הקהל הנפלא שלקח מזמנו ובא לשמוע קצת על הרצאה שתתאר לכם את נפלאות היקום. הנושא של ההרצאה שאני אתן היא על אסטרונומיה בקרני X, כן? קרני רנטגן, אני תכף אזכיר לכם מה זה, אבל אני רוצה לחזור למה שהציג פרופסור סרפוד יותר מוקדם, על העובדה שכשאנחנו מסתכלים על היקום אנחנו צריכים להחליט איזה משקפיים אנחנו שמים. כמו שילדים משחקים עם משקפיים ירוקים, כחולים ורואים דברים אחרים, אנחנו כאסטרופיזיקאים יש לנו טווח הרבה יותר גדול של צבעים להסתכל בהם. והצבע שאני אסתכל בו איתכם על היקום היום, זה הצבע של קרינת הרנטגן. זוהי השמש. קרינת רנטגן לא מזכירה בשום דבר את איך שנראית השמש באור רגיל. אז רק שיהיה ברור על מה מדברים, רנטגן גילה את קרני ה-X, אנחנו קוראים להם, עוד בסוף המאה ה-19, ומהר מאוד היו אפליקציות רפואיות שכולכם מכירים. התמונה פה היא התמונה של טבעת הניסויים של גברת רנטגן. אנחנו לא יכולים לדמיין את הרפואה המודרנית בלי קרני רנטגן. אבל לקח למעלה מ-100 שנים, מאז שרנטגן ב-1901 קיבל את פרס נובל הראשון לפיזיקה. נובל ניתן לריקרדו ג'קוני פה ב-2002 על אסטרופיזיקה בקרני X. למה זה לקח 100 שנה? אז התשובה היא ברורה, צריך להגיע לחלל. זה יפתיע אתכם אולי לשמוע, אבל האסטרונומיה של היום היא לא מאוד שונה מהאסטרונומיה של לפני אלפי שנים. אתם רואים פה כמה אסטרונומים מפורסמים מההיסטוריה. אנחנו חוקרים פחות או יותר את אותם דברים. אלא מה שהטכנולוגיה שעומדת לרשותנו היום היא בסדרי גודל יותר ממה שעמדה לרשותם. ובהקשר הזה של קרינת X, בוודאי של הכנס פה, הבדל של שמיים וארץ, תרתי משמע, הוא היכולת להגיע לחלל. אז מצד ימין ריקרדו ג'קוני עם טלסקופ בקרני X, וטלסקופ בקרני מיקרוגל מתחת, ופרס נובל שניתן לג'ון מת'ר, הפרס נובל הראשון אגב שניתן לחוקר מנאסא, על קרינת הרקע הקוסמית. אז שוב, רק לסבר את העין, זה הספקטרום של הקרינה האלקטרומגנטית, וכפי שנאמר פה קודם, כבר רק מעט מאוד חודר את האטמוספירה. למזלנו כאנשים שחיים פה, אבל דאבוננו כאסטרונומים שמנסים להסתכל אל החלל. חוץ מהאור הנראה שאתם ודאי יודעים, אפשר לראות את הכוכבים, כמעט כל אורכי הגל האחרים בעצם לא חודרים. אז באנרגיות המאוד נמוכות, זה מסודר פה משמאל לימין באנרגיה, יש לנו את קרינת המיקרוגל והאינפרה האדום הרחוק, הזכירו אותה קודם, עליה אני לא אדבר. באנרגיות יותר גבוהות, אני הולך פה ימינה, יש את קרינת הגמא ואת קרינת ה-X שעליה אני אדבר היום. בצד שמאל של הגרף אתם רואים גבהים, אז ברור לכם, אין לי פוינטר, אני מקווה שהאחבר יעבוד, זה הגובה שמטוסים מגיבים אליו, זה עשרות קילומטרים, בלונים, טילים ולוויינים. כמובן שעם לוויינים היום אנחנו יכולים לעלות מספיק גבוה שאנחנו יכולים לראות את העולם כפי שהוא נראה בעיניים האלה של קרינת רנטגן. זה גם שינה לגמרי את ההתנהגות של אסטרונומים. יש פה קריקטורה שמראה 3 אסטרונומים מתחרים בכמה הם לא אסטרונומים קלאסיים. הראשון אומר, אני אף פעם לא משתמש בטלסקופ, השני אומר, אני אפילו לא מתקרב לטלסקופ, והשלישי אומר, אני אפילו לא טורח להסתכל למעלה. אז זה אומנם בבדיחות הדעת, אבל זה באמת המהפכה שעברה האסטרונומיה מאז הימים שהיה צריך לבלות באיזה לילה קר, על איזה הר, בשעות לא שעות. היום בזכות הלוויינים אנחנו מבצעים את המדע בצורה אחרת לגמרי. זה 2 טלסקופים גדולים, או הגדולים ביותר שנמצאים היום בחלל, קרינת X, צ'נדרה של נאסא, ו-XMM ניוטון של סוכנות החלל האירופאית, של איסה. טלסקופים ענקיים, כן, של 10 מטר, הרבה יותר גדולים מדברים אחרים שאתם מכירים בחלל. כבר נמצאים בערך 10 שנים, ורק היום אנחנו מתחילים למצות את המדע שאפשר לקבל מהם. רק שתבינו מה הסיפור, אז צ'נדרה לדעתי עד היום מחזיק את השיא, הטלסקופ צ'נדרה מחזיק את השיא של הפיילוד, של המשקל הכי גדול שעלה על המעבורת. מהמעבורת היה צריך עוד שיגור נוסף, זה בטן המעבורת לפני השיגור, והטלסקופ נכנס למסלול. המסלולים של טלסקופי ה-X הם מאוד מאוד רחוקים מכדור הארץ, מאוד אליפטיים, מגיעים בנקודה הרחוקה ביותר מכדור הארץ בערך לשליש המרחק מהירח. אז ברור לכם שזה לא דומה לטלסקופ החלל האבל למשל, שאפשר להגיע אליו בכמה מאות קילומטרים, לטפל בו, לתקן, להחליף דברים. פה כדאי שהכל יעבוד כמו שצריך, כי אי אפשר להגיע. ומסתבר שהיקום אומנם מלא במקורות X. יש פה איזו גלריה של תמונות מטלסקופ החלל של צ'נדרה. בעצם כל דבר שיש בשמיים היום אנחנו יודעים הוא גם מקור של קרינת X. לא תמיד זה נראה לנו כמו אותו אובייקט באור נראה, אבל אם זה כוכבים, אם זה גלקסיות, אם זה חורים שחורים, אם זה כל דבר שיש בשמיים, מסתבר שגם פולט קרינת X, מה שכמובן עושה לנו הרבה מאוד עבודה בתור מדענים. אז הנה רק דוגמה לחשיבות של טלסקופ חד. צ'נדרה זה הטלסקופ הטוב ביותר מבחינת יצירת תמונות וחדות תמונה. אתם רואים מצד שמאל איך נראית תרפילית הסרטן עם צ'נדרה. הרזולוציה או כושר ההפרדה הוא של 0.5 שניית קשת. הדבר הזה הוא די מדהים. שניית קשת, למי שלא יודע, זה 1/3600 של מעלה. כלומר, תיקחו מעלה, תחלקו אותה ל-60, יש לכם דקה, עוד 60, יש לכם שניית קשת. וההפרדה היא יותר טובה משניית קשת של צ'נדרה, אתם רואים משמאל, ולדוגמה מצד ימין, את הטלסקופ הכי טוב שהיה לפני. בשביל להשוות את הרזולוציה הזו לטלסקופים אופטיים למשל, אז מצד ימין יש פה סדרה של תמונות בכתום מטלסקופ החלל של האבל. ככה נראה תרפילית הסרטן בין אור נראה. מצד שמאל אתם רואים את תרפילית הסרטן בקרינת X. זה אחת הדוגמאות שבהן התמונה היא לא מאוד שונה. אבל אני מביא את הסרט הזה, שהוא בעצם כמה תמונות אחת אחרי השנייה, בשביל להראות שהרזולוציה היום, ההפרדה שמגיעים בקרינת X, היא כמעט כמו ההפרדה שמגיעים באור נראה. הדבר הזה הוא פשוט מדהים. אז בואו ניתן עוד כמה דוגמאות של אובייקטים. אז זו, כפי שאמרתי לכם, השמש, באור נראה נראית כמו עיגול צהוב, די משעמם, אני חייב לומר. בקרינת X אנחנו רואים שיש אנרגיה מגנטית מאוד חזקה מעל פני השמש. מה שאתם רואים למטה בשחור זה בעצם פני השמש. עוד פעם, מקווה שהאחבר יעזור לי. פה זה השמש, היא שחורה בקרינת X, תמונה בקרינת X, אבל כל הפעילות מעל השמש נראית בקרינה הזו. הדבר הזה כמובן חשוב לנו, השמש היא הכוכב האהוב עלינו ביותר, והקרוב אלינו ביותר, מטעמים למשל של רוחות שמש. הרוחות האלה שאתם רואים פה מצולמים עוד פעם בקרינת X, בצד ימין, מגיעים כדור הארץ. מגיעים לכדור הארץ, עושים מה שנקרא שערות מגנטיות, יכולים להפריע לתפקוד של לוויינים, נתפסים בשדה המגנטי של כדור הארץ, מגיעים לכתבים ויוצרים את זוהר הצפון. יש היום תעשייה שלמה, אפשר לקרוא לזה של מזג חיזוי, מזג אוויר מהשמש, וחשוב כמובן לעשות את זה באנרגיות של קרינת X. השמש גם מתפרצת בקרינת X, אתם רואים פה התפרצות מאוד חזקה על פני השמש. אז אם ההרצאה של פרופסור סאופורד דיבר איתכם על האינפרה האדום, זה היה החלק היותר רגוע ונינוח של היקום. כשאנחנו הולכים לקרינה באנרגיות גבוהות כמו קרינת X, אנחנו בעצם מסתכלים על היקום הרבה יותר אלים. איפה שמשתחררת, אלים במובן החיובי, של איפה שמשתחררת הרבה יותר אנרגיה. כמה מילים על ככה, מה שאנחנו יודעים על היקום ואיך הגענו לפה. בשביל להגיע לחיים יש הרבה מאוד שלבים שצריך לעבור. ואני מפרט אותם פה מאוד בקצרה. היקום כמובן צריך להיווצר או להיוורט, תלוי בהשקפת העולם שלכם. מבנים ביקום, גם הם הוזכרו קודם, צריכים להתפתח, גלקסיות. אני תכף אראה לכם צבירי גלקסיות. היסודות צריכים להיווצר. אנחנו יודעים שביקום המוקדם אין יסודות כבדים שאנחנו עשויים מהם, אלא רק היסודות הקלים של מימן והליום. ואחר כך צריכות להיווצר מערכות פלנטריות ולהיווצר מולקולות אורגניות וחיים בצורה שאנחנו מכירים. כל אחד מהשלבים האלה הוא כמובן עולם ומלואו, אבל אני רוצה לשים את הדגש על שני שלבים שאנחנו רואים בצורה יוצאת מן הכלל באנרגיות גבוהות. וזה השלבים של יצירת מבנים, איך נוצרים המבנים ביקום, ואיך מתקבלים היסודות, איך מתקבלים היסודות הכימיים שאנחנו עשויים. אני אתחיל דווקא עם השני. כאמור, יסודות כבדים, פחמן, חמצן, חנקן, אלה שאנחנו מכירים ומוכירים פה כחיים על פני כדור הארץ, לא נוצרים ביקום המוקדם, אלא הדרך היחידה שאנחנו כאסטרופיזיקאים יודעים שהם נוצרים בהם זה בליבות של כוכבים. תוך כדי בעירה גרעינית, מיזוגים גרעיניים בלב הכוכב. לצערנו, לראות לתוך כוכב זה בלתי אפשרי. מסתכלים על השמש, אי אפשר לראות את הריאקציות הגרעיניות האלה במרכז. מתי אנחנו כן רואים את התוצרים של התהליכים האלה? כשהכוכב מתפוצץ. מה שאתם רואים פה זה כוכב שעבר סופרנובה, פיצוץ של כוכב, כעבור כמה מאות או אלפי שנים אפילו אחרי הפיצוץ. זו תמונה שנלקחה עם טלסקופ החלל של האירופאים, XMM ניוטון, וכל תמונה זה 9 תמונות בעצם של אותו אובייקט, בצבעים, אם אתם רוצים, של אקס-ריי, אורכי גל קצת אחרים, שמתמקדים ביסודות שונים. אז למשל, שתי התמונות העליונות, זה תמונות שנלקחות בחמצן, תמונות אחרי זה נלקחות ביסודות כמו סיליקון, כמו ברזל וכן הלאה. ככה אנחנו יכולים ממש לעשות ניתוח כימי של התוצרים של הכוכב. ואם אתם שמים לב, בקצה השמאלי העליון של הסופרנובה, פה ישננו, הנה פה יש נקודה בהירה שמופיעה רק בשתי התמונות האלה ולא מופיעה בתמונות האחרות. זה חמצן טהור. ככה אנחנו בעצם עושים דיאגנוסטיקה כימית של מה שקרה בלב הכוכב, אבל רק אחרי שהוא התפוצץ והוציא את כל הקישקע שלו אל התווך הבין כוכבי. לתת לכם מאזן של יסודות, או לא של יסודות, של חומר ביקום, אז היום כבר אסטרופיזיקאים יודעים שהרוב הגדול של היקום מבחינת אנרגיה זה אנרגיה אפלה. ואני לא הולך לדבר עליה, אנחנו לא ממש מבינים מה היא. אנחנו רק יודעים שהיא גורמת ליקום להאיץ בהתפשטות שלו. חומר קצת פחות מוזר זה החומר האפל. חומר אפל שאנחנו מזהים אותו דרך הגרביטציה שלו, ותכף אני אראה לכם. וישנו את החומר הרגיל, שהוא החומר האטומי. בואו נקרא לו בקיצור אטומים. החומר האטומי, מסתבר, הוא בערך 5% מתחולת האנרגיה של היקום. גם את 5% האלה אנחנו כאסטרופיזיקאים לא מצליחים למצוא את כולו. שאלה אחרת ומעניינת בפני עצמה זה איך אנחנו יודעים את המספרים האלה, אבל תתפלאו כמה אנחנו יודעים אותם במדויק. גם מתוך 5% האלה של החומר האטומי הרגיל, אנחנו לא מוצאים אותו. אני רוצה להראות לכם איפה אנחנו חושדים שהוא ואיך אנחנו מתיימרים למצוא אותו. התוצאות שאני אומר לכם פה זה ממש מאמר שהתפרסם השבוע וחם מהתנור. מה שאתם רואים פה, תכף אני אסביר לכם איפה מתחבא פה החומר, זה מצד שמאל תמונה אמיתית של היקום בטלסקופ. אתם רואים הרבה מאוד גלקסיות, צפירי גלקסיות, כוכבים, כל מיני מקורות. מצד ימין יש סימולציית מחשב של היקום. ככה תיאורטיקאים מבינים שהיקום צריך להיראות, נותנים ליקום להתפשט ולמבנים להתחיל לקרוס, ומיד מזהים שחוץ מהמקורות הבהירים, כן, אתם רואים פה צפיפויות גבוהות, שזה כנראה אזורים עם הרבה גלקסיות, ישנם גם החוטים האלה שמקשרים אותם, מה שאנחנו קוראים הקוסמיק ווב. את החוטים המקשרים אנחנו לא מצליחים לראות בטלסקופ. הסיבה לזה היא כנראה שהם מאוד מאוד דלילים ומאוד מאוד חיוורים ופשוט לא פולטים מספיק אור. זה כמובן לא אומר שהם לא נמצאים שם. שם אנחנו חושדים שנמצאים אותם אטומים חסרים, אותם אטומים גז רגיל שאנחנו לא מצליחים למצוא. מהי השיטה לזהות דבר כזה? כמו שאמרתי לכם, פליטה מהגז הזה אי אפשר לקבל, הוא דליל מדי. השיטה זה להאיר אותו מאחורה, כן? לשים פנס מאוד חזק בצד השני של היקום, ולהסתכל איך הפנס הזה, איך האור מהפנס הזה עובר דרך התווך ומגיע לטלסקופ שלנו, כאשר חלק ממנו, מאוד קטן, נבלע. מה זה הפנס הזה? הפנס הזה לצורך המחקר הזה, זה מתפרצי קרינת גמא. ישנם ביקום, ישנה תופעה של התפרצויות קרינת גמא. תדמיינו את הדבר הזה כמו לשבת במרכז של אצטדיון, וכל רגע יש איזה פלאש ממקום אחר. הנה סימולציה שהכינה נאס"א להמחיש את העניין הזה. הסיבה שאנחנו רוצים את ההתפרצויות האלה כי הם מקורות אור מאוד מאוד חזקים, ואם נתפוס אותם בזמן עם הטלסקופ, נוכל לבצע את הניסוי הזה של בליעה של המקור לאורך בעצם כל היקום. ההתפרצויות האלה הן במובן מסוים ממש בצד השני של היקום. אנחנו משתמשים במקורות האלה באמצעות טלסקופ מאוד מתוחכם שנקרא סוויפט, אתם רואים אותו פה בפינה, וכשמו כן הוא, זריז, והיכולת העיקרית שלו זה היכולת להסתובב מיד ברגע שהוא מזהה התפרצות כזאת. הנה פה המחשה של הטלסקופ, יש עליו, חוץ מהגלאי קרינת גמא, יש לו טלסקופ X-ray, יש עליו גם טלסקופ רגיל, ומסתובבים מאוד מהר אל המקור. ההתפרצויות האלה לפעמים אורכות כמה שניות וכדאי להגיע לשם מהר. המהנדסים שביניכם, אז שמתי פה כמה מספרים, צריך לסובב את הטלסקופ, הוא מצליח לסובב אותו בערך ב3 מעלות לשנייה ולעצור אותו פונקט על המקום בדיוק של דקות קשת ופחות מזה, תוך כמה שניות. באמת הצלחה הנדסית מסחררת. ברגע שהטלסקופים מזהים את המקור, אנחנו יכולים למדוד ספקטרה, ולפי הצעת פרופסור סארטווד מתחילת היום, אני בעצם לא אראה לכם ספקטרה, זה קצת משעמם, אני אראה רק דוגמה אחת. וזו הדוגמה הזו. הקו האדום בעצם מראה איפה את המקור היה צריך להיות אם הוא היה מגיע אלינו כמו שהוא נפלט, והמעט הזה שאתם רואים פה חסר קצת בצד שמאל, פוינטר לא עובד, בקושי עובד, צד שמאל אתם רואים קצת חסר קרינה. עכשיו שתבינו, כמות החומר שבולעת פה, אני אגיד לכם את זה, זה ממש, זה לא יאמן, זה בערך מטר של אוויר. כן? כמות אוויר שיש לכם במטר, קחו את המטר הזה של האוויר, תפרסו אותו על כל היקום. זה האפקט הזה של הבליעה שאנחנו מצליחים למדוד פה, בזכות הטלסקופים באמת היוצאים מן הכלל. אנחנו ככה בעצם גילינו את אותם אטומים שעד היום אי אפשר היה לראות אותם. אפילו סימנתי עיגול שיראה איפה הקרינה החסרה. נושא אחרון שאני אעלה היום, יש לי מעט זמן אני יודע, ולכן אני אהיה קצר, זה הנושא של צבירי גלקסיות ושל חומר אפל. צבירי גלקסיות זה המבנים הכי גדולים ביקום, כן? תתחילו מקטן, תחשבו על כוכב, כוכב יש 100 מיליארד בגלקסיה, זה גלקסיה. יש לנו גם צבירים של גלקסיה, שיש בהם מאות, לפעמים אפילו אלפים של גלקסיות. זה בעצם המבנים הכי גדולים שיש לנו ביקום. אנחנו היום יודעים שהצביר הזה מורכב מ3 חלקים, 3 רכיבים יש לו. חלק נכבד, שזה יותר מ-80%, זה החומר האפל. ותכף אני אסביר לכם איך אנחנו מזהים אותו. חלק שני בחשיבותו, זה גז חם שיושב בין הגלקסיות. אתם רואים בתמונה הזו מין הילה כחולה כזו, שיושב מסביב לגלקסיות. זה לא בעיה של התמונה, זה תמונה אמיתית באקס-ריי. חזרנו לקרינת הרנטגן. תמונה באקס-ריי בעצם הרבה מאוד גז חם שיושב בין הגלקסיות. וכמובן את הגלקסיות אתם גם רואים כנקודות בתמונה הזו. זה הנקודות הצהובות הקטנות. הגלקסיות עצמן הן רק 3% מהחומר. איך אנחנו מזהים את החומר האפל? אנחנו מסתכלים על הגז החם, ואנחנו יודעים שמשהו מחזיק אותו לא לקרוס. כי הגרביטציה הייתה רוצה לגרום לגז ליפול פנימה. מה שמחזיק אותו כלפי חוץ הזה לחץ. את הלחץ אנחנו יכולים למדוד. תסמכו עלינו שאנחנו רואים תמונה כזו, אנחנו יודעים למדוד את הלחץ של הגז שם. מה שמאזן את הלחץ החוצה זה הגרביטציה, ואנחנו יכולים לחשב כמה מסה יש. זה באמת חישוב די פשוט, יש גם דרכים אחרות לחשב ולמדוד מסה אפלה. המסה הזאת קוראים לה אפלה, כי יש שם הרבה יותר מסה ממה שאנחנו רואים בטלסקופ. הדוגמה הזו היא דוגמה מאלפת של 2 צבירי גלקסיות כאלה, שבעצם התנגשו. למה הדוגמה הזו היא חשובה? אני אחזור על זה תכף, כי ישנן תיאוריות שמתחרות בתיאוריה של חומר אפל. אפשר למשל לומר, ויש כאלה אנשים רציניים שאומרים, המסקנה של חומר אפל מבוססת על זה שאתם חושבים שאתם מבינים את חוקי הכבידה. לוקחים את החוקים של ניוטון. אם חוקי הכבידה לא לגמרי מדויקים ומשתנים בכאלה סיטואציות אסטרופיזיקליות, אז בעצם לא צריך חומר אפל. אז אני רוצה להראות לכם פה דוגמה מאלפת לעובדה שחומר אפל כנראה קשה להתחמק ממנו. יש פה שני צבירים שהתנגשו, אחד בשני, ועכשיו בואו נחשוב רגע על שלושת הרכיבים האלה. רואים אותם בתמונה בשלושה צבעים. יש לנו את הגז החם באדום, שאתם רואים הוא יושב באמצע. יש לנו את החומר האפל, שתכף אני אסביר לכם במקרה הזה איך אנחנו יודעים לחשב אותו. ויש לנו את הגלקסיות, שאותם הכי קל לראות. החומר האפל, במקרים של צבירים מאוד חזקים, אנחנו מודדים באמצעות עידוש גרביטציוני. אני אעשה את זה רק בזריזות, רק שאתם תסמכו עליי שאנחנו יודעים לעשות את זה. אנחנו רואים שאם יש מקור שיושב מאחורי הצביר, לפי תורת היחסות הכללית של איינשטיין, הצביר עצמו מעקם את הדרך של האור, והאור מגיע אלינו כמו דרך עדשה. אתם רואים את הטבעות האלה, שמזהים פה בצדדים של הצביר. דרך זה אנחנו יכולים לחשב כמה העדשה הזו חזקה, או במילים אחרות, כמה מסה יש בה. אז אנחנו יודעים למצוא את המסה, וזה אתם רואים פה עכשיו דווקא בעננים הכחולים האלה. אנחנו יודעים למצוא את הגלקסיות עצמם, והן יושבות בתוך העננים הכחולים, אתם רואים משני הצדדים. אבל באמצע יושב גז חם, שהוא עיקר החומר האטומי. למה הדבר הזה קורה? החומר האפל, כשאחד עובר דרך השני, שני צבירים כאלה, לא מרגיש אחד את השני, שקוף. גלקסיות גם הן מאוד, מאוד קטנות, עוברות אחת דרך השנייה. הדבר היחידי שבאמת מתנגש, זה אותו גז חם שאנחנו יכולים לראות עם טלסקופ של אקס-ריי. והדוגמה הזו היא דוגמה מאלפת, כי רואים שהגז, עיקר הגז הוא הגז החם, יושב באזור האדום, אבל עיקר המסה, עיקר החומר, יושב דווקא במקום אחר. יש ממש הפרדה במרחב בין איפה שיושב החומר האפל, שיושב החומר הקורן, וקשה להתווכח עם התוצאה הזו, עם איזושהי תיאוריה אסטרופיזיקלית שמנסה להימנע מחומר אפל. אני חושב שבזה סיימתי, אני לא יודע כמה עוד נשאר לי, אבל תנו לי להגיד מילת סיכום. אסטרופיזיקה זה לא מה שהיה פעם, ובמיוחד אני רוצה לכוון פה לקהל הצעיר והקהל של הבית ספר. אנחנו בפסגה של הטכנולוגיה, אנחנו יודעים להסתכל על היקום היום מהאורכי גל הקצרים ביותר, שזה בקרינת גמא, לאורכי גל הארוכים ביותר, של קרינת המיקרו וקרינת הרדיו, ולקבל תמונה מקפת של איך נראה היקום. חלק נכבד מזה זה היציאה לחלל. אחת השאלות שנשאלת תמיד זה, טוב, איך אתם, ישראל הקטנה, יכולים באמת להשתתף בחוויה המדהימה הזו? אז צריך פה להגיד בבירור ולהודות לסוכנויות החלל שמאפשרות לנו להשתמש בטלסקופים שלהם, לא כטובה, זה נאמר פה קודם, אלא כחלק מהתחרות הבינלאומית. אנחנו מציעים תצפיות, מקבלים זמן מתוך תחרות מאוד מאוד קשה, אבל אני בצניעות הראויה אגיד שהאסטרופיזיקאים בארץ הם מהטובים בעולם, ולכן אנחנו עומדים בתחרות הזו, מרוויחים זמן או מקבלים זמן, ועושים מחקר כמו כל אחד בכל מקום אחר בעולם. אז תודה רבה לכם על האתנחתא הזו מהחיים האמיתיים.
תודה רבה. בתור ישראלי אנחנו דופקים אותו ולא נותנים לו מתנה. ואני רוצה לנצל את ההזדמנות בזמן שמחליפים פה מחשבים להציג את המרצה הבא. Our next speaker is Dr. Anthony Colaprit from NASA Ames, and he'll talk about the new exciting discovery of water on the moon. And we are moving, Dr. Colaprit got his first degree in physics, University of Colorado in 1992, and his doctorate at the University of Colorado in the year 2000. And spent 3 years as a NRC fellow at NASA Ames and decided to stay on at Ames. It's a beautiful place. And has been ever since. He's now in the planetary science branch of Ames Research Center. Dr. Colaprit, please.
Thank you very much. I'm used to mumble mics, so if I back away from this, just yell at me and move forward again. It's a real pleasure to be here, and the word was used, humbling, and it's certainly for me, when I saw the list of speakers that I was going to accompany, I was shocked and awed and really humbled. And this is a really interesting conference for me. I'm very much used to going to scientific conferences, and often you're in your little session with a very focused topic, and this conference has such a broader consciousness which is really exceptional. And I think important for us scientists to actually appreciate and step away and come away with to actually help bring science to a broader community and bring that broader community into the fold of the science we do. That's really a big part of our job as well as the science we do. So what I'm going to talk about are some really interesting discoveries over the last decade and how our view of the moon, that object just right outside that we see every so often when it's clear, is really, really changed. And it's just changed in the last decade or so, and it's changed in no small part to a huge international cooperation. And that's what I'm going to describe today. The moon, just a decade ago, was really what I would call the Apollo era moon. I was born on July 16, 1969, actually, when Apollo 11 launched to the moon, and got into planetary science in part because my father worked on that mission, among other space missions. And what we always understood of the moon was it was generally a constant place. It was very interesting from a planetary perspective and how it related to the Earth, but it was gray. It looks gray. It was pretty constant. It had an atmosphere, an exosphere of maybe argon and some sodium and potassium. And it had very little water. It was generally considered bone dry. And we knew this basically from the remote observations and the sample returns that we got from the Apollo and then Soviet sample return missions. Not all those samples, though, showed that it was completely dry. The Apollo samples did suggest it was very dry. The samples returned showed maybe 10 parts per billion in terms of water concentration. However, some of the samples, one in particular from Luna 24, showed somewhat higher concentrations, and that was very intriguing. It showed concentrations at about 0.1%. This observation, though, was pretty readily dismissed back in the mid-1970s. And later, in the 1980s, from ground-based observatories, Faith Vilas, a colleague friend of mine, made some observations of the moon and discovered that, indeed, in the near-infrared, in some spectral regions, she saw what looked like water absorption. And she worked hard to get this published, and finally it was published in a rather obscure journal, and no one really thought much of it or didn't care to hear about it. They kind of dismissed it as, oh, that's just fanciful thinking. But there was still hope for water, and that goes back even way before the Apollo program. We knew early on that the moon didn't have much of a tilt to its rotational axis, so the sun at the poles never rose above the horizon by more than a few degrees. And that meant if you had any topographical relief, that shadows would be cast, and some of those shadows, regardless of the season of the moon, would be in the same spot regardless. And so in the bottoms of craters, it was thought you could potentially have areas that saw no sunlight for as long as that crater was there, and as long as the moon's tilt was what it was. And so that potentially meant these craters' floors, the floors of these craters, may have not seen sunlight for 1 billion or 2 billion years, and therefore probably pretty cold. So it was thought, well, water ice or water of some form could exist there, but we had no evidence for that as of yet. So I just explained to you how water could be stable at the poles, and it was believed that these craters could be cold, but we never actually made temperature measurements of the moon until very, very recently. The Lunar Reconnaissance Orbiter, it's a NASA orbiting spacecraft that's in orbit around the moon, brought a thermal radiometer, an instrument that could measure temperatures. And these were the first real temperatures globally, in particular of the moon, and could measure temperatures as cold as what we thought the craters could be. We thought the craters could be maybe 100 degrees or colder. Kelvin, 100 degrees Kelvin. And that's important because at 100 degrees Kelvin, water ice is stable even in a vacuum over long periods, say 1 billion years. And what we found was that actually in the bottom of these craters, it is really cold. This is an image from the North Pole, temperatures from the North Pole of the moon, the large crater in the middle, Perry crater. And in some of these craters, we're seeing temperatures as low as 30 degrees Kelvin, 25 degrees Kelvin. Actually now, on the moon, the temperatures measured are the coldest temperatures observed on any planetary or other surface in our solar system. They are potentially cold. They are colder than the predicted temperatures at Pluto, which we will measure in a few years here. So right in our backyard at the moon, we have actually the coldest places in our solar system, which is quite amazing. And also the potential reason why water could ever exist potentially on the moon. So why would we even care? Why even then, 40, 50 years ago, did we even ask the question of water, and why are we so interested in it now? Well, there's really two reasons that I can think of. They're broad reasons, and I think they come equally mixed, meaning they're both equally important. The first reason is water as a resource. Those of us who are interested in exploration in human exploration, in particular beyond Earth's orbit, beyond the moon, and out into our solar system and beyond, need to understand how to work with resources found locally, in situ. How do we get someplace and take advantage of what we have there to actually enable extended exploration by humans, or even extended exploration by robotic systems? So water, a critical resource, is important to understand, and how you access it and how do you utilize it. The second real important reason is its scientific value. Finding water on the moon and understanding the source of the water, how it got there, how it's evolved, what its flavor is, if you will, is really important to understanding the history of our inner solar system. The moon and the Earth are, of course, tied to each other, and I like to compare it to ice boring here on Earth. When you go to an ice sheet, a Greenland ice sheet or in Antarctica, and you can drill down tens of meters, you actually look back in time, because that ice has been there, frozen in place with everything else for those hundreds of thousands of years potentially, and you can actually extrapolate time backwards and understand the climate of Earth backwards in time. Now think if you could do that with ice that is potentially 2 billion years old, and that's what we might have on the moon. And so the moon is potentially holds a climate record of the inner solar system, the things that have happened to Earth, to Mars, Mercury, that could actually have a lot to do or tell us a lot about the formation of our oceans, the formation of life even on Earth. So the discovery of water on the moon and the future studies of it could potentially really shed light on our inner solar system. So people were interested in water and the moon for other reasons, and some missions went there in the 1990s that actually reinforced this possibility. And I show them here two of them. The first was a Clementine mission. It was a very small Department of Defense, U.S. Department of Defense mission that carried some science instruments. And then another one was a NASA mission called Lunar Prospector. These are both very small spacecraft. Lunar Prospector actually never even had a computer on it. It was all just a solid-state, very simple spacecraft. The two spacecraft, though, did find things that made us more interested in the possibility of water at the poles. First, the Clementine spacecraft did an experiment with radar. It had a radar on it, and what it did was, as it flew over the south pole of the moon, it shone its radar at the lunar surface, and a radar dish on the Earth at Arecibo recorded that data. And what they were looking for was the reflection, the strength of the reflection of the radar. And what they found as they passed over a crater called Shackleton, which is right near the south pole of the moon, they saw a strong reflection of this radar. And in particular, they saw an increase in a particular quantity called the circular polarization ratio. And that basically is just a measure of how strongly a radar is actually reflecting and scattering off the surface. Water, when it's pure, can very effectively scatter radar. And so this got them very interested. Well, something in Shackleton reflected the radar very strongly. It's a dark crater. Shackleton's known to have a permanently shrouded floor, so it's probably cold enough to hold water ice. That's interesting. The only problem here is it's not a unique measurement. If you look at the moon from other Earth-based radars, you can find high CPR, high reflection areas in bright, warm regions. And these are probably areas where you have talus slopes, rock slides that have fallen and created equally as reflected facets of rock as you would see in water ice. So it was interesting, but it wasn't at all conclusive. Lunar Prospector had a neutron spectrometer on it. A neutron spectrometer measures neutrons that are emitted from the moon naturally, cosmic galactic rays come in and interact with the lunar surface and kick off neutrons from the surface, and that's what this instrument measured. Hydrogen is a very good attenuator, absorber of neutrons at particular wavelengths or energies in particular. And what it could see was where those neutrons were absorbed by hydrogen, and that's what I'm showing here. These are two figures of the total neutron flux from the moon from that instrument. It's the North Pole and the South Pole. North Pole on the left, South Pole on the right. And the areas that are blue are areas where there was decreases in neutron flux, meaning something, hydrogen, we knew it was hydrogen, was more plentiful there, absorbing neutrons. Now the problem with this instrument was you just knew it was hydrogen. You could not say what form the hydrogen was. We didn't know if it was water. We didn't know if it was just captured protons from the sun and from the solar wind. And if it was water, we didn't know the form of the water. Was it just adsorbed water or water in the mineral makeup, in the mineral matrix? Was it just hydroxyl bound in minerals? Was it water ice? We just didn't know. All we knew was, indeed, some thermodynamical stability of hydrogen is occurring at the poles of the moon. And I say thermodynamic stability, meaning, yeah, it's probably in the cold traps. But again, the resolution of this instrument was so poor you couldn't say specifically what crater it was or was not in. Well, that was up to the end of the 1990s, and then started the new century. A plethora of spacecraft flew to the moon, and really has changed our view of the moon in many, many ways. And I show this timeline here, just showing how international the lunar exploration program has been. And I've often said that, or it's been said that the last century was really the golden age of astronomy, where astronomy has really come to age, and discoveries really benefit from the advent of new technologies. Well, I think planetary science now is going to be entering a golden age, and I think it's not necessarily because of new technologies, but actually because of the contributions of multiple nations into the program. It takes a lot of resource and capital and human will to fly planetary missions. And the more nations and peoples involved with it, the more you can do and the more your return will be. And this example of the moon's exploration of the last decade is a real good example. So, keying off those observations of potentially high radar in Shackleton Crater, the Japanese satellite, Kaguya, took some images of that crater, and they were actually able to see the crater floor. If it was a permanently shadowed crater, meaning the crater floor sees no sunlight, how could they do that? Well, they used scattered light. There was light that comes down at the rims of the crater and scatters, and some of that scattered light enters into the crater floor. And so they just took some very overexposed images at select seasons and were able to reconstruct a composite image shown up there in the upper right-hand corner. And what they basically concluded was, well, we don't see any ice rinks. There's no ice in there. And they looked at the reflectivity of the surface and said, well, most likely there's not large amounts of water ice in there. But we really couldn't tell. They looked at some other craters, and it's actually, this technique's hard. You can't use it at all. It's like all the dark craters to see in the interior. But it still was inconclusive as to whether or not water ice was there. About a year and a half ago, the Indian spacecraft, carrying an instrument built by NASA called the Moon Mineralogical Mapper, or M-Cubed, much easier to say, observed the moon at visible and near-infrared wavelengths. So it looked in all the visibly lit regions and was mapping the mineralogy of the moon. And one of the things it was looking at was an absorption band out at the longer wavelengths that was interesting. It was difficult to get at because you had to do some delicate removal of thermal effects, but one of the spectroscopists made the figure on the left one Saturday. I actually know the fellow, and he was telling me about the moment he made it, and he plotted it up, and it came up on his computer and said, wow, the moon's got polar caps. And what this is showing is water absorption in the minerals, hydroxyl, OH, and or water, H2O. And since then, they've made a map more completely of the entire moon. That's what's shown on the right. And anywhere you see blue or magenta or cyan is some form of hydroxyl or water. bound in the mineral. Now, this is the kind of stuff that is at the 0.1% level. So that Luna 24 sample and the earlier ground-based observations, they've been rediscovered and remapped globally on the moon. And it just shows there is water all over the moon globally at some low concentrations. Now, also on the radar, on the Indian spacecraft, was a radar. Also, a similar radar is on the Lunar Reconnaissance Orbiter. And it was trying to repeat the experiment that Clementine did, looking for that high backscatter. And it has some very interesting results for the North Pole of the Moon, as was shown here. Basically, they found that there's two crater types. The one, on the figure in the top right, shows a variety of craters at the North Pole seen in radar. The lower left corner shows a fresh crater. What you see is the crater and an ejecta blanket spread out around it. It's all bright because it's all reflecting the radar equally well. The crater on the right is a different crater. It doesn't show that ejecta blanket around it. It only shows a bright scatter from the interior. So this is consistent with large slabs of ice. And to get this kind of reflection, you need literally 2 or 3 meters of relatively clean, pure ice, meaning like 80 or 90% pure ice. So it could be buried maybe beneath the surface by 10 centimeters or more, but it has to be slab ice to make these kinds of reflection. Again, it is not a unique indication of ice, so it's a bit speculative. So NASA, along with the Lunar Reconnaissance mission, tried to come up with a mission that could be a little bit more definitive as to whether there is as to what the form of that hydrogen is at the poles of the moon. And they came up with the LCROSS mission. It was a competed mission, and I was the principal investigator who proposed it. Be careful what you wish for, as they say. And it was a mission of opportunity. So the mission itself was an experiment. NASA wanted to find out if it could build a quick, low-cost, relatively low-cost mission, planetary mission, not just an Earth mission, but planetary mission. LRO was going on to a larger launch vehicle. It had some extra throw weight to the moon. So they said, let's hear what you can do with it. By the way, you only have so much money, and you only have 24 months to do it in. And so we won the competition. The administrator basically said, I want to see if this even works. I want to see if you even get to the dance with this. And that was the agenda for us. What the LCROSS mission was to do was to bring some of that dirt up from one of those permanently shadowed craters. Bring dirt that hadn't seen the light of day in 1 billion or 2 billion years and bring it into sunlight so we could see it. And bring material from depth up. Part of the problem is some of that water ice could be buried. And so no matter how hard you look from above, you'll never see it until you actually excavate some of it. So that's what we proposed to do. And the trick here was not to bring our own impactor, but to use the spent upper stage of the Atlas V rocket we rode on, the Centaur, and use it as an impactor. So LCROSS was, as I mentioned, a real experiment in itself. It was what we call a capability-driven mission. So scientists often don't like to work this way, but what we did was we said, okay, these are our goals. What exists that most closely matches our scientific measurement goals? And we met often somewhere in the middle. We did what was good enough, not what was better. And one of the engineers basically put it, well, we got to find stuff that we can glue together. We can't develop anything new to meet this schedule. We have to find stuff to glue together. That simplified our requirements. We worked to simplify the design wherever possible. One of the things that I think relevant, in particular to this conference, that we did on the payload was we worked with non-traditional industry providers. I remember one traditional instrument provider calling me up and saying, hey, I hear you got a mission. I'd love to fly an instrument. How much, what's your budget, and what's your schedule? And I told them, and they said, thank you, goodbye, and hung up. And so we had to find non-traditional vendors, and we did. And one of my favorite stories is the instrument that discovered water ice on the moon's former use was carpet recycling and beer quality control on assembly line plants. So we went to industry partners who had never had spaceflight experience. One of those vendors who worked for a commercial spectrometer product line said, I asked him, I have a very short development schedule. Can you get it done in 6 months at the engineering unit? And he said, 6 months? Why that long? And he said, we make money with product on the showroom floor. Our development cycle is 3 months. And indeed, they got us an engineering unit for flight that we got into our qual testing in 3 months. The schedule at the bottom shows a typical NASA design project schedule. This is for the managers out there who like this stuff. We did not do away with, we could not, NASA wouldn't let us, do away with any of the peer review or internal review process or quality control, but we were still able to fit it all within 12 months. And again, it came back to the requirements, simplifying design, simplifying requirements, and doing non-traditional procurement and development of the payload and spacecraft. And it worked. We came in ahead of schedule and under budget. Here we are attached below on the left, below the Lunar Reconnaissance Orbiter. The LRO's got the gray blanket. We got the nice gold blanket. You can see one of our non-traditional parts of our spacecraft, the giant gold ring, looks kind of like a sewer pipe. We built the spacecraft basically around the mounting ring, adapter ring, to the Atlas V rocket. That's certainly, you can imagine the Lunar Reconnaissance Orbiter said, well, you selected a secondary payload. You only gave them a little bit of money. You said, be ready real quick, and you're sticking them between us and the rocket. Great. That made them feel very secure and rest assured that they weren't going to have any problem on launch. And the rocket, that was 5 shown there on the right. The white upper stage is the Centaur. That's the part we held onto. It's normally ditched into the ocean. We held onto it and used that as our impactor. The payload shown here, a total of 5 cameras, 3 spectrometers, and a radiometer. Go through this quick so we get some results. And an image of the ejector plume, kind of hard to see on this screen. We went into the crater Cabeus, which is down there on the lower right. For scale, the entire crater is about 100 kilometers across. The ejected cloud at about 20 seconds was about 10 kilometers across. This image was taken with a video camera called Rocket Cam. It flies on rocket flights all the time. It was no larger than a dry eraser marker, about this big. And it was taken from about 600 kilometers away. So we used really simple cameras to do really important science that you wouldn't otherwise think NASA doing. And yes, I have a spectra. I'm sorry. As a spectroscopist, I like to show them. This shows actually some water ice detection in the ejected cloud. We have wavelength in microns across the bottom and the relative brightness running up the y-axis. And what this shows is basically a model fit to data. The little circles with the air bars are the data. The red lines are a combination of various species that we fit to the model. And right at the 1.5 micron mark, you see a nice strong feature consistent with water ice grains. So this was the first time we had very definitive evidence that inside these dark craters there is indeed water ice. We also found hydrated minerals and OH. So where we are now is there's no longer a question whether or not the moon has water. What we found now is, wow, the moon has a lot of different kinds of water in all the different forms, distributions, and concentrations. We have everything from the very low concentrations seen globally. We have then the kind of stuff we saw inside of Cabeus, where we impacted, we saw about 5% by concentration mass water ice. I should say, too, we saw all sorts of other wonderful things. It was discussed, the hydrogen sulfide and the other formaldehyde and hydrocarbons that were the building blocks of life. We saw that trapped, as you might expect, at 40 Kelvin. Where we impacted, it was about 40 Kelvin. So anything that can freezes out there. And then on the extreme end, we have the possibility of this slab ice. So the question isn't really now, is there water? It's really, it's much more complex than I think we ever really appreciated. This usually happens. We have a very simplistic view, take some measurements, and then suddenly our simple view is thrown out. We have to understand how these are all related. And right now, this is where we're starting now. There's a whole rebirth of lunar science and lunar scientists now looking at this and will be looking at this for many years to come. So a final conclusion sign here, it's really the same moon. But we've really had a revolution of our understanding of the moon and how water is related to it. And this is just one of many discoveries that all these missions have made of the moon, but I think one of the most important in how it will actually play into our future and the future of exploration beyond the moon. We understand that it's widespread. It comes in a lot of different distributions. And it is a viable resource to be used, and it is a viable scientific tool. And that's actually important, too. It begs the question, how do we balance our needs going forward in exploration and science so that they mutually benefit from each other? So where we are now is trying to understand the source of the water, what it means, and extrapolate beyond. And in the coming years, there are many other missions planned. For NASA, we have the GRAIL mission, which is 2 orbiters that will orbit the moon and measure the gravity to unprecedented level. And we have another orbiting mission called LADEE, a Lunar Atmospheric and Dust Environment mission, which will measure the dust and atmosphere over the moon. And it will actually be looking in part how water migrates around the moon and through the exosphere. There's a number of international missions too planned, rover missions, lander missions, etc. So the moon is a new place, and we're just now starting to really explore it for the first time. Thank you.
We've now reached the last talk of this session, and it's a very different talk. Professor Fabio Marazzi of Emeplus, which is a law firm, will talk about innovation and research in the European market, the Italian view. Professor Marazzi is a well-known expert in innovation and internationalization in the fields of life sciences, nanotechnology, and aerospace and defense, and has recently been appointed on the board of directors of Expo 2015 SPA, and will tell us a little bit about how to get innovation and research and how it's done in Italy. Thank you.
Thank you very much. It's a great pleasure to be here. You may be wondering why a lawyer after such a lot of big and interesting science. Probably it's because after having found ice and water on the moon, the next step would be to go looking for a lawyer on the moon immediately after. I'm going to talk about, very briefly, about the EU support to the research and innovation. Since 2003, the space sector became more and more important in the European context, initially with the publication of a white book on the space, and afterwards with the agreement between the European Space Agency and the EU, European Union in 2004, which has been mentioned this morning by the General Director of the European Space Agency. This agreement is aimed to govern the relationship and to define the line of cooperation between the two entities. And finally, we had two pieces of regulation in place just now. One is the resolution of the European space policy adopted in 2007, and the other one is the resolution taken forward the European space policy adopted in the Council on 2008. Both resolutions mention the definition of tools and mechanisms suitable for the future action of the European Union in space sector. And moreover, as reminded this morning by the General Director of ESA, in the Lisbon Treaty, the space sector is included in the EU competences. Therefore, each member state and each member country can define our own national space policy. In this general and very scientific framework, we can see the European space policy, the European space program, and the activities related to the research framework program. The key messages enunciated into the European space policies, as you can see, are to improve the coordination of the civil space programs between the European Space Agency, the European Union, and member states, to develop and to exploit the European Space Programme Galileo and GMES, to maintain an independent European space access, to invest in order to preserve the technological expertise and the knowledge in the science and in the exploration, and to maintain a European industry competitive in the development and in the production in the space field, and finally ensure an efficient cooperation between the European Space Agency and the European Commission, and identify a coordinating mechanism between European Space Agency, European Union, Member States, and for international relationship activities. The second resolution I've mentioned before, the one for 2008, confirms the ESP principles defined in the third Space Council resolution, inform about the progress achieved and detect the future priorities for European space. And they are space and climatic changes, space contribution to the Lisbon strategy, space and security, and space exploration. The resolution foresee that Europe became leader in the space global scenario and consequently invite the institutional actors involved in the process to work together and in synergy. One of the major tools in order to support research and innovation in Europe, as you probably know, is the framework program. The research framework program, the one in place right now, the FP7, was launched in 2007 and will end in 2013. The general budget was fixed at that time in 54 billion euros for 10 topics, including space and security, for which the specific budget was 1.5 billion euros. For the next period, the so-called FP8, the budget could reasonably increase. And by the way, as you probably know, Israel is one of the non-European country partners of the framework program for Europe. Financial activities in the workspace program are space application, satellite development, observation systems, GMS systems, for the environmental protection, security, civil protection, risk management, space exploration, support of the activities developed by the European Space Agency and national agencies, and enforcement of the Space Foundation support of research. Regarding the application of space technologies in different sectors, technological transfer is a sum of different activities directed to the use of space technologies, which have been transferred to other producing and of service context, and aimed at enhancing technologies which have already been developed, and at their future re-utilization within context not properly belonging to space. At the national level, technological transfer is one of the areas of focus of Italian Space Agency, which plays as a facilitator in marketing activity. In particular, the Italian Space Agency is involved in analysis and monitoring of development trends in the Italian and international market, classifying the portfolio of Italian goods, products, technology, application and space services, ensures the areas of potential development for the space market and technological transfer, selecting opportunities for acquiring intellectual property patents for the agency from relevant activities and develop them, ensuring the diffusion of space knowledge toward potential user pools and toward Italian decision-making center, and managing, finally, systematic relationship with effective and potential user of operational center and technological product and space application, promoting the development of synergies and the exchange of information among industries, university, research center, and financial institutions. At European level, as mentioned this morning, European Space Agency Technological Transfer Program Office has successfully transferred over 200 space technologies to non-space sector for application as diverse as, for example, cooling suites for a Formula One racing team, ground-penetrating radar to detect cracks in mine, tunnels, and several healthcare innovations. The activities of the European Technology Transfer Program have also led to the creation of a number of new startup companies in Europe, many of which have been promoted through ESA business incubators. The main mission of the Technology Transfer Program at the European Union is to demonstrate to the European citizen some of the benefits of the European Space Program and to strengthen the competitiveness of the European industry. European industry is strengthened by encouraging the beneficial as well commercial use of space technologies for non-space application, which in turn leads to innovative products and the generation of new jobs through public funds, and for which it's possible to carry on a transfer of technology towards fields of the Earth market, which would get an advantage from new technology. Insofar as for financing activity is concerned, space agency efforts will be exclusively directed to adapting the technology to the identified market. At the same time, technology transfer from fields not pertaining to space to those of space is of utmost importance. Developments of activities from Earth to space, the so-called upstream model, is in fact the most attractive opportunity to exploit the SME's potential in terms of innovation. In this last case, it's necessary to encourage the improvement of technology, which were hereto exclusively for Earth use. Transfer of technology from Earth to space is based on the ability to pinpoint innovating and stable technologies utilized in Earth markets which could be applied in the space field by way of appropriate adaptations. Field from which it could be possible as well as desirable to acquire new technology to be transferred to space are mainly electronics, precision mechanism, tools and materials. This last type of technology transfer model, the upstream, is very interesting for a country like Italy. In the focusing on SMEs, we have to make some consideration about the really particular type of the productive manufacturing system that we have in Italy. 80% of the total amount of the enterprises in Italy are SMEs. Only 10% of them are innovative companies. What it means? It means that in a modern economy and in the global market, in which the time to market needs to be drastically reduced, a large part of Italian SMEs considered alone are not competitive. But what happens if we put these SMEs in a different context, supported and connected with universities, public research institutions, and big companies? It's easy to say. In this way, the SMEs can maximize their work and their knowledge, having a new role in the market, better say, the old role, but now shining again. This is what is happening and what could happen in the space sector. The dynamic in the space sector can be and should be a case study for the interaction between the public sector, the high technological industry in the Italian economy. The revenue of Italian space industry is 1.5 billion euros per year. More than 35% is produced by SMEs. The work of SMEs is referable to activities connected with research and development, for instance, in ground segment, software development, which is so important, or in the so-called downstream in the production of application or the utilization of the satellite data, and so on. At the moment of the underutilization of European funds by the Italian SMEs, but this is a phenomenon in quick reduction. In conclusion, since the Italian technology in many of the space branches is very high, and Israel at the same time has a very high technology level in many other sectors that could apply to the space sector as well, it could be very interesting to set, as it was recently set, a collaboration framework between those two countries, in particular in order to support SMEs, in order to approach the space sector as a business opportunity, and to increase the friendship and the relationship between our country and Israel. Shalom.